Thanks. Okay, so today I'm going to briefly introduce the work that me, Sean, and other people in the group like Peter are carrying out in the Gravity Laboratory that is about analog cosmology. With this work, what we propose is a classical to fluid system that we use as an analog model to examine some of the effects of the preheating phase of the early universe. I'm going to now just give a general idea of the, of the cosmological background by starting with the reheating. Reheating is a phase of the cosmological scenario during which is a process that describes basically the production of the particles of the Standard Model. And this process takes place right after the exponential expansion represented by inflation. So basically, at this stage, what happens is that the inflaton field leaves the flat region of its potential and starts oscillating around its minimum. In this region, the inflaton field will transfer its energy density to the other scalar fields coupled to it. And in particular, if this process happens by inducing parametric resonance in these modes, then we have preheating, the so-called preheating. So basically, basically what we see is that the amplitude of these modes are going to increase exponentially through time, which means on a physical level that we have a rapid production of particles. The theory of preheating, what we expect to see in for this theory is that initially, we will observe the exponential growth of a primary mode. Then that primary mode will decay in the production of secondary modes, secondary stabilities, which means basically that there is a even bigger production of particles that will lead the universe towards thermalization. We aim to observe exactly this kind of effects. In order to do that, though, since we are not able to observe directly this kind of phenomena, we have to use an expedient. This expedient is given by analog cosmology in this case, which allows us to reproduce some of the key aspects of these cosmological scenarios in laboratory-based experimental setups like the one that I'm going to describe here. Okay, so I want to now stress why it's possible to make this connection between the fluid system and the cosmological theory. What happens is that the analogy is based on the presence in both systems of this parametric resonance. Parametric resonance is a phenomenon that happens when we when a system exhibits instabilities when subjected by to an external periodic force. In particular, if we linearize the solution of this motion, we obtain Mathieu's equation. And Mathieu's equation is central for our study. In fact, it describes exactly how, on one side, the interaction between the inflaton field and the fields coupled to it happen. And on the other side, how the dynamics of the azimuthal modes on a fluid system will evolve, basically. And of course, we're considering a fluid system that is subjected to an external periodic force, and we will see the appearance of Faraday waves, modes or instabilities that will be parametrically amplified. A couple of words about our setup. So our setup is composed by a biphasic solution of with aqueous phase and organic phase. These two fluids have different densities, and such that basically if we mix them after a while, what happens is that they're going to separate out, and in particular the organic phase is going to sit on top of the aqueous phase by creating an interface between them. Then what we do is to drive externally and oscillate vertically this system, and what we study is exactly the dynamics of this interface between the two fluids. In particular, we're going to study its dynamics in the nonlinear region, such that we can have some more insight, learn something about preheating as well. Okay, so here we have a picture that represents a reconstruction of data from our system where we see that the top fluid, the lightest fluid, is transparent, basically. Okay, now some about the observations that we had. Okay, here there is a plot that shows the behavior of the amplitude of the primary mode respect to time. And we see distinctly the different stages of our experiment. So we start from an initial phase where the detection scheme noise is overwhelming the whole signal. Then we start driving externally our vessel. And what happens is here, as you can see here, this primary mode will be excited and will undergo parametric resonance and exponential growth. But this growth doesn't last indefinitely. In fact, the system will reach at a certain point this. Okay, I think it might be out of. Okay, well, it reaches the nonlinear regime where the different modes in the fluid system will start interacting with each other. And in this phase, the approximation we made to obtain Mathieu's equation are not valid anymore. So we observe breakdown of the parametric instabilities, and basically what happens is that the amplitude of the primary mode will stabilize, and this mode will decay, let's say, in the excitation of the secondary modes. Finally, we will have that in this red region, that we shut off the external force, and the excited mode will decay back to equilibrium. So now to just conclude, basically what we observed through this research is that we're able to observe some of the key features of the preheating cosmological scenario by reproducing them on a hydrodynamical system composed by two fluids. And Sean now is going to briefly talk about our current goals, which is basically to reproduce some of the other characteristic aspects of different cosmological scenarios, such as the thermalization of the universe, or what happens if we apply an external magnetic field on our setup. So, yeah, that's it. Thank you. Gonco. Yeah, we'll answer the questions later, I think.
How do I touch this?
You have to just like this. That's okay.
Cool. Okay. So now I'm going to talk a bit about what we've been using our experimental setup for, and that is the study of universal scaling dynamics. So I'm going to tell you a bit about what that means. Say we have some system that we prepare in a sufficiently far from equilibrium initial state and then leave it to thermalize. It will pass through an intermediate period of self-similar evolution that we call the scaling regime. Now, the scaling regime is a fixed point attractor solution, meaning that so long as the initial conditions were far enough away from thermal equilibrium, it will pass through the same scaling regime regardless of the details. This insensitivity to the exact details of the initial conditions are where we start to see the effect of loss of information during the thermalization process. So what are these self-similar scaling dynamics, other than a bit of a mouthful to say? Well, these are dynamics that can be effectively described by a simple scaling relation. For a homogeneous and isotropic system, the relevant scaling relation is the one here, where these alpha and beta are called the scaling parameters, which are parameters which have some relationship that depends on the details of the system. Now, I've only had to tell you that the system is homogeneous and isotropic in order to specify this form of the equation. And as such, we expect this equation to apply to a wide variety of physical systems. This is the concept of universality, and universality is what we exploit in analog cosmology. So in our case, we expect to see the same dynamics occur both in cosmological preheating as we do in the nonlinear evolution of our interfacial modes in our fluid mechanics experiment. And of course, a fluid mechanics experiment is far more accessible than scalar fields in the early universe. So not only is it a fantastic test ground for understanding the general phenomena, but it also gives us an insight into the cosmological scenario. So here's what scaling dynamics look like in practice. On the left, we have a graph showing some simulated data for a free two-dimensional system. we see that at low momentum scales, the distribution function follows a power law behavior, whilst at high momentum scales, it deviates away from this power law. We also see that during the scaling regime, the distribution function decreases with time at the low momenta, whilst increasing with time at the high momentum scales, as energy is transported up to the high momentum scales in the system. We can verify that this is indeed described by the scaling relation on the previous slide by rescaling the momentum along the x-axis and the distribution function on the y-axis by these factors of time over some reference time raised to the power of alpha and beta respectively. Doing so collapses the distribution function plotted at different times into a single curve, as can be seen up the top right here. So this is what we're currently looking for in our experiment. The last thing that I'd like to talk about is our future plan for improving upon our experiment. So specifically, we want to apply a magnetic field across our interface in order to study an expanding space-time background. So why do we want to do this? Well, our current experiment simulates a scalar field theory on a 2+1 dimensional Minkowski space-time. Now, this is conformally equivalent to the equation of motion for a scalar field theory on an expanding FLRW space-time once we redefine the field to incorporate the scale factor and work in conformal time rather than physical time. So this is great because we can learn something about the expanding cosmological case by looking at an effective metric that's stationary. However, the details of the expansion are obscured in this mapping. So this is because we're working in laboratory time for our experiment, which serves as an analog for the conformal time and not the physical time. So we can't see any inherent effects of the expansion of the universe, such as, for instance, mode freezing upon horizon exit. In order to do so, we need an explicitly expanding background. But this seems very challenging, right? How can we somehow expand the size of the vessel of our container mid-experiment whilst also keeping the balance between the two fluids just right so that the interface maintains intact? Well, fortunately, we don't need to do this. We have a clever workaround which relies on the fact that the expansion of space is equivalent to the slowing of the speed of light. Now, that may seem confusing at first, but let's take a look at the Minkowski metric, where we have modified the speed of light to be time-dependent. If we identify this time-dependent speed of light with the reciprocal of the scale factor, we can pull it out the front as a global factor such that the effective metric now reads as the FLRW metric up to a global factor of 1 over a squared. In our system, the wave propagation speed is our analogy to the speed of light. So if we find a way to make this wave propagation speed time-dependent, we can produce a system with a FLRW effective metric. The way we're planning on doing this is to replace the upper fluid with a diamagnetic material, the lower fluid with a paramagnetic material, and then to apply a strong magnetic field in the radial direction across the interface. Doing this introduces a magnetic potential term in the Euler momentum equation that governs the dynamics of the interface. The magnetic field will be produced by an electromagnet that we have a high degree of control over. So by changing this through time, we make the magnetic potential time-dependent also. This in turn induces a time dependence on the wave propagation speed in the subsequent equations of motion. By doing so, we can create a system with an effective FLRW metric of an expanding spacetime. So to summarise what we've talked about, here at Nottingham we are simulating a 2+1 dimensional effective field theory by using the interface between two fluids of different densities. We can induce parametric resonance on this interface in order to study cosmological preheating. The specific aspect of cosmological preheating that we are currently interested in is that of universal scaling dynamics. And finally, we have future plans to upgrade our experiment in order to simulate a more realistic cosmological scenario. So thank you very much for listening, and let us know if you have any questions.